So, brain itself. We know that the brain functions differently than, than you probably think. Most people think of the brain as one thing, correct? People say, oh, your brain. You think of like this spongy lump in your head, right? Is it one thing? No. I heard, I think his name was Steven Pinker, he described it more as, it's almost like a bunch of organs, like your organs. All right, so if I looked at your body, I'd be like, yeah, that's your body. But your body's not just one thing, right? It's a whole bunch of organs that work together to make this thing move and grow and all of that. Your brain's very similar, and that's why I had you guys do the anatomy of the brain first, so you at least had a kind of understanding that different parts of the brain have different roles. I mean, you're not experts on it, neither am I, because there's way more than we learned about that anatomy portion. But just understand that your brain itself, it's more like a series of interdependent organs, or you can say regions too. There are certain parts that are actually separable. I can actually remove them, and I'll go on living. But will I be the same? No, it's going to affect my behavior because there's not like one. Well, sometimes there's one thing I can look at, but if I change my brain, it's going to change the way those parts all interact. That's going to change how I see and perceive, behave, and so on and so forth. So over time, we've really come to understand that, again, your brain's not just like one thing or two, even in hemispheres. It's like a bunch of little parts that all have a certain role or opinion or influence, and that can actually vary depending on how they communicate or interact with the other parts of it. All right, so I give you an example right off the bat. The brain itself. So let's do a side view and an overhead view. So you kind of know what I'm talking. It's not quite that much like an apple. All right, whatever. Okay, here's an example. If I want to figure out, how can I phrase this? We know that certain regions have certain roles. First, by noticing people that had damaged brains or parts of their brain. All right, I think in the notes, was the Phineas Gage guy in the notes?
Yeah.
Okay, that's one of the most famous examples. Since we didn't have like this advanced technology to like look at images of the brain and how the energy moves and how it works before the 1960s, we kind of had to guess. Like you can't like look at someone's brain and see how it works because it's in them, right? And if you take it apart, they'll almost certainly die, depending on how you do it. So you can only see after the fact. Be like, if someone behaved a certain way, you could look at them after they die and see if their brain's different, but that could just be, it could have happened after death, you don't really know. The best way to know what a brain does or doesn't do, or what parts of it, is to see somebody who went from being one way, then had some sort of head trauma or brain damage, then all of a sudden they were forever different. All right, and Phineas Gage is one of the famous examples of that. He was somebody who would bore holes in rocks and put the dynamite powder in there and set it off and blow the rocks apart in the 1800s. And I guess one of the times when he was using the rod, it like sparked and caught the dynamite stick, and then it blew up. And before he could even react, because it's so fast, it's almost like a bullet, not quite that fast. It just the steel rod went through his eye and out the top of his head. All right. Now you would think that would kill you, right? It didn't, though. He didn't die of infection for whatever reason, so yay his immune system. He didn't bleed to death, yay his blood clotting and all of that. But afterwards, people noticed he was much different. He could still do math, he could still talk, he still moved and ate and was normal, but something was different about him. He went from being a soft-spoken, patient, kind, nice person to all of a sudden being a very immature, angry, mean-spirited person. And like, why the hell is he acting different? They didn't understand. All right, we know now, at least partly, why he totally changed after that. So he's, again, functions perfectly normal as a human being, except he acts completely different.
Did they take the rod out like they?
Yeah, no, he just lived his whole life with a rod in his face. Yeah, I don't know what they did. They probably gave him a glass eye, and I'm sure he's disfigured after that. But nonetheless, people noticed he was much different. And it wasn't just because he was mad that he was disfigured. He was forever changed.
Isn't that called a lobotomy?
A lobotomy is where they disconnect your frontal lobe. I forget exactly which region, but I know for sure they disconnect your social reasoning and reasoning portion. So people often end up becoming immature and impatient and angry. So I don't know exactly what region of his was damaged, but I know it was in the frontal lobe, and it was partly, so up here. I know for sure because he no longer was able to stop himself from saying mean things and being a mean person and being patient. He almost certainly damaged part of his ventromedial prefrontal cortex. So I'm actually zoom in because the cortex, the frontal cortex, we just learned the frontal cortex. You can actually divide that into a bunch of mini regions too. So we don't have to know these for the AP test, but I'm going to tell you so you have a little understanding of it. All right. So the ventromedial prefrontal cortex is here-ish in this region, roughly speaking. And if you looked at it from above, it's kind of like this. That has many roles, but one of the things it does is your inhibition control. Anybody know what that means?
Like impulse control, or like if a bad comment pops in your head and you'll actually say it.
Exactly. So it could be impulse control because you have an impulse to say something mean. But yeah, that's what kind of puts the brakes on it. Like you want to say something mean or do something mean or violent or aggressive or whatever. But depending on the situation, this is largely what stops you or lets you keep going. So for example, if, I don't know, Conor McGregor was here and he did something to me, the odds that I'm going to speak up, I don't want to say challenge him, I would never challenge him, obviously, because he would just whoop me. But part of the reason why I would never challenge him, like let's say he came in and did something terrible, right? And normally I should be like, get out of here or willing to, fight for myself or whatever. I'm probably not with him because I know he or any UFC fighter would I'd be a rag doll to them. They're trained, they take hits, they're strong, they're better conditioned, like I have no chance. Unless I have a weapon, but I don't have a weapon, I'm just here at school. So if he came in and started like bad-mouthing me or throwing my stuff around, well, I'd probably just have to leave because I can't do anything about it. I'd call the cops certainly, but I wouldn't be able to directly stop him, all right? I might have the urge to, but why wouldn't I? I just told you why. Yeah, I'd have no chance. I'd just get whooped. Any UFC fighter I would, right? Because I'm not trained like they are or anything. So what actually stops me is that frontal cortex, specifically the ventromedial prefrontal cortex. That's my brakes. That's the one that looks at the situation and goes, no. I know you have the desire to stop him, but you cannot. You'll actually hurt yourself more by trying to stop him. Just call the police or go away or whatever. All right. So if I have that damaged, or maybe I'm born with one that's not properly connected or not wired properly or whatever, I'm going to, from that point on, or if I'm born with it like that, I'm going to have really, really bad impulse control or inhibition. So when a desire comes up that might not be a good idea at the time, whether it's saying something or doing something, that's what stops me. And if that's damaged, I am way less likely, if at all, to stop myself from doing that thing, whether it's something violent or saying something mean or doing something inappropriate or whatever. All right? You'll never guess what they find when they scan the brains of violent prison inmates. You'll never guess what they find out about their frontal cortex. Got any guesses?
That what's it called?
You can just say frontal cortex,
The frontal cortex
Mhm.
probably damaged.
Yeah, or in their case, it's less active. Now, it could have been damaged at some point, we don't know that. Or they were born with a situation where there aren't as many neurons there, it's not as connected, it's not as active, whatever. Nonetheless, when they scan the brains of these violent criminals that are in prison, they overwhelmingly have very inactive regions in this frontal lobe, specifically in that area, right? So if I were to scan a person that's of a normal average behavior, I would see activity there in those circumstances when you see these violent inmates, the ones that repeatedly get into violent altercations in prison. Those regions are way less active, if active at all, compared to a regular person. All right. Is that if I can scan a brain and see that one region's working, one region's not, and that causes them to do something or not, would that be a social reason or a biological reason? Yeah, that would be much more biological than social, right? Now, social does play into it, right? Because that's what your brain does. It analyzes the situation. Because if it's, well, I shouldn't use fighting as an example. I'm not going to use fighting as an example. Let's say, we'll just use verbal aggression in this case, okay? So, let's say, you've got somebody, I wouldn't do this, but I think you understand the situation. Let's say you are talking to somebody and they say something that is inconsiderate or mean or disrespectful about you. Maybe even it's unintentional, but they say it. If it's a stranger or somebody on Twitter, what are the odds that I'm going to respond back with something? High or low? Okay, it kind of depends on the person. But I guess I should give you the two situations. There's a situation where it's a stranger. All right, let's pretend they're not like bigger than me and they don't have a gun or anything. It's just, we keep using the internet example. They'll never see me at all. It's on Twitter. All right, so something on Twitter happens. They say something mean. Am I more likely to respond with something mean then, or am I more likely to respond with something mean to somebody like my boss, or I personally would, but like my boss or somebody who's going to invest in my company, or maybe they even said it unintentionally. Which one am I more likely to be mean in?
Twitter.
Yeah, the Twitter one, right? Because there's no consequence. Well, there's little consequence for that, right? So that's definitely a social factor. But what's considering that factor, like, oh, this person, I have to work with this person, or I see this person, as opposed to some random person on Twitter or some person on Twitter I don't see often. Your frontal lobe is going to be the one that determines largely if you do that or not, because you're still going to get the aggressive response from your amygdala, which is in your limbic system. That's going to be like, say something, respond, aggression. And then this is the one that slows it down and says, whoa, 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 let's look at the situation. And then maybe, sometimes it lets it go, maybe sometimes it doesn't, maybe sometimes it tones it down, whatever. That's the part of your brain that does that. So if it's not active, then all you get is this, the anger part, with nothing to stop it, or a lot less of a chance to stop it. All right, so you guys understand that? All right, sweet. Let's pause with that for now, take a break, and then I'll finish up this explanation after. Neuroscience is basically the study of how the brain works, and we use scans, which I'll get to in a second. But the discoveries by this neuroscience has increasingly discredited the 100% social explanations for all of our behavior. Not only do we come with some already intact instinctually, like, for example, infants, even though before they've learned anything, there's still something pre-programmed in them that understands what a solid object is. So if I take, like, for example, when they show infants like brand new, 2 months old or less, or 3 months old or less, they can't talk, they can't understand anything for the most part. They still understand what objects are, and they're confused if you show them illusions that break the rules of physics. So for example, if they show them like a video of a wall and then a ball goes into it and then just goes through the wall, like, I don't mean like breaks a hole in it, I mean like just passes through it, the infants are intrinsically confused by that. They also intrinsically understand like cliff edges. So I'm not saying just let your kid be on the edge, he won't fall off, but they do have a good understanding intrinsically of what a cliff is. Doesn't mean they won't fall off of it because they're clumsy and then they stop paying attention, but if they are paying attention, they'll see that and they'll know that I will fall off of that. If you show them videos of things appearing out of nowhere and disappearing out of nowhere, they're confused by that. So they have this intrinsic understanding of how physics works born in. They don't even have a chance to learn it yet. But anyways, more about behavior specifically. Thank you, sir. Before they had scans, they really had to look at brains that had damage to them to know what parts did what. So we know with Phineas Gage, he got the spike through his frontal cortex, probably in this region. It was damaged, and he no longer had the ability, or less of an ability, to stop himself from saying or doing things that were inappropriate or mean or be patient and nice, all right, because that was damaged forever. He no longer had the same brakes for those impulses to be mean or impatient. They also discovered language is the same way. So there's two areas of your brain. I don't know if it's in the notes or not. And they're named after the guys that discovered them, by the way. So there's the Broca area, which is roughly here on the side. On the left side, by the way, not the right side, the left side. And the Wernicke area, which is here-ish. They found that people with lesions or damage to these regions, whether it's like a cut or a tumor or some other type of damage, they couldn't process or articulate language. So the Broca area here, that's roughly speaking how you articulate your words. So the fact that I'm able to sit here and just spout words out to you guys to express what I'm trying, the message I'm trying to cross, that's almost all, not all, but most of it's coming from my Broca area. And if something were to happen, I were to get a tumor there, or damage there, or cut there, I would no longer be able to formulate my words, at least properly. All right, I don't know what the effect would be on me at 32. I don't know what parts of it have to be damaged, but damaging this region would jeopardize or eliminate my ability to articulate thoughts. All right. So what do you think the Wernicke area has to do with language? Understanding it, right? All right. And I'm oversimplifying, but that's roughly what they are. If I were to experience damage to my Wernicke area, that would cause me to struggle with or eliminate my ability to comprehend language. So what I'm hearing and reading and things like that. And it would just go away permanently.
So do many people like that part's damaged, the Broca thing? Is it damaged?
Oh, it might be. I don't know if, I don't know specifically, because there's lots of different connections. I don't know if a person's born without the ability to speak, which would be in particular, because then you'd have to ask, well, can they write it? Is it a vocal thing? Do they understand it? So you'd have to look at lots of different factors. But yeah, that would and could be a contributing factor. All right. So yeah, and how would they know this, by the way, that these regions do this before brain scans? What's the only way they could know? I already told you.
They're damaged.
Yeah, if they're damaged, right? There's a lesion on it, tumor, cut, whatever kind of damage. So patients that had this couldn't do these things. So they know that, well, clearly your brain has specific functions. This is sort of them discovering, even back as far as the 1800s, that your brain's not just one organ, it's more like a system of organs that are networked together and interact with one another to actually cause you to think and do things. All right. And it gets increasingly complicated. So this frontal lobe portion, I'm going to focus on this for a second. This is, there's also a dorsomedial, which I'll get to in a second, but this is, among other things, responsible for your judgment, so making decisions, planning. I know that sounds like super elementary and fundamental, but like most animals can't plan. Most animals plan on accident. Like they have some instinct to constantly burrow nuts in trees and bury them, but they don't actually remember where all of them are. I don't know if you guys know this, but when squirrels are storing acorns for the winter, they're not doing it consciously. They just have this urge to do it because 80% of the acorns they store they never find again. They just happen to come across them. But the squirrels that have that instinct to randomly hide acorns all over are the ones that end up living because they find some of them during the winter, and the ones that didn't do that die off. So they're not actually like planning it per se. But we actually planned. We go, well, last year, let's pretend this was 10,000 years ago. Last year, when the sun was this high in the sky, it got colder and it was harder to grow things. So I should probably try to either move or keep other food sources so I can live through the winter next time. I hate this damn phone. Yeah. Sure. Thanks. Bye. So loud. You too. ASAP. Yeah, I've only got 2 minutes left. All right. I forgot what I was talking. Oh, so here we go. Planning. This is where my problem solving is. So, like, if I want to achieve a goal, like I want to go home. There's a problem, right? I'm at work currently, so I'd have to find someone to cover you guys. If I didn't have a vehicle, that would be a problem because I can't walk, 20 miles or whatever realistically every day. so I had to figure out a way to get a ride. I mean, I have a car, but if I didn't, that's what my problem solving is. Like, here's my goal, go home. What are my obstacles? I have responsibilities with you guys. It's a long distance. That costs money. So my problem solving would be my ability to find somebody to cover for you guys, and let's pretend I didn't have a car, find an Uber or take a bus or something like that. That's what your problem solving is, all right? It's also goal setting. It's also, a lot of your speech is in that region too, so I could just say speech, but it's really just the left side of it. What else is it? Oh, your social reasoning. You're like, what's that? Oh, just your reasoning in general, I should put. Your morality, your sense of morality. That's all up in there in that frontal lobe. All right, so your sense of what's right and wrong is up there. What I mean by social reasoning, by the way, this is a good one to focus in on for biology and behavior. Social reasoning is my ability to understand the mood you are in and how that's going to impact your behavior. All right? So if I see that you're frowning and you're all tight and you're short with your words and you have this very intense look, what does that tell me? You're angry, right? Maybe anxious, but probably angry. So you're in a bad mood. You're angry. Does that affect how you are going to act, the person that's angry?
Yes.
It is, right? They're going to take in information differently, perceive it differently, and respond differently. Does that mean if I want to interact with that person, I'm going to have to probably act differently than I normally would if they were not angry?
Yes.
Yes, I know it's a long question, but it's complicated. Seeing that somebody is upset without them telling you is social reasoning. You see their body language and behavior, you analyze it, then you predict how that's going to affect their behavior, and you adjust your behavior accordingly to get what you want. So example, I'm you guys, let's say I'm you, and I want to, I don't know, go to a concert in the city, San Francisco, over the weekend. Some of your parents would be cool with that. I bet some of your parents wouldn't be cool with that, depending on who's going and all of that. All right, so let's say it's just you and your friends, and it's at night. The odds that many of your parents would say yes to that are very low, I imagine. Some of you, maybe not. But let's say my parents would say yes in normal circumstances. If I go to ask them like, oh, sweet, yeah, I heard about this, let me just go ask my mom, and I go down and I see she's angry. What am I going to do? Not ask her then, right? That's your social reasoning, right? You've understood the situation, like, I want something. Mom's in a bad mood. Not a good time to ask mom, right? So you would wait till she's at least normal, if not in a good mood, because people are more likely to say yes if they're in a good mood, right? Which is that interaction between society, like how they actually are, and then your ability to analyze that, which is biology, determines your behavior as you go through, all right? There is a specific region of your brain that is responsible for that social reasoning. And that's the dorsolateral prefrontal cortex. Again, you don't need to know that. Just know that the frontal cortex does these things. But that's here-ish. So it's like kind of above the ventromedial prefrontal. Dorsomedial prefrontal cortex, among other things, is your social reasoning. So what would happen, do you think, if genetically I was born and there was an error in my genes, or I just inherited a gene or whatever, and that part of my brain when I was developing as a child didn't connect, or didn't connect properly or fully, or it was damaged in an accident? Is that going to affect my behavior?
Yes.
It absolutely is, all right? That is what most autistic children on the autism spectrum, most of them have damaged or not normally functioning or wired differently, whatever, less or more active, or less active in this case, dorsomedial prefrontal cortexes. They, depending on where they're on the spectrum and what degree of activities in that region, they struggle to understand the moods, or what's the word I'm looking for? It's called theory of mind, where you can see how somebody is based on their emotional state and predict how they're going to act. They struggle with that, or they can't do it at all because they've lost that part of their brain. And you can tell them what mad means, and that mad means that they're going to do this, but that's the best they got. They'll never be able to recognize it in somebody, all right, unless you specifically tell them. That's why, generally speaking, depending on who you're dealing with, but you have to be very specific with people on the autism spectrum, particularly if they're further along the autism spectrum. because they are increasingly less able to read other people and their intentions. All right? To them, you are just a wind-up doll, and they don't know how to tell. Because most dolls, you can't change their expressions and things like that. Some of you can. But if I have just like a standard Barbie doll, if Barbie's mood changed, would I know on the Barbie doll? No, you wouldn't be able to see it. So that's kind of what it's like for somebody who has a damaged or malfunctioning dorsal-medial prefrontal cortex. They can't read you. They don't know what mood you're in. They don't know what's going to happen. They can't predict it. All right, so it makes it really hard to interact with people. That's why they'll say things that are insulting sometimes. Like if their mom's like let's say their mom's crying, and they're like, "Oh, you look terrible," or they'll say something like that because they don't understand the mood they're in, how that they're less receptive to that, or even that that's mean per se, because they don't understand how their actions affect you. They can't comprehend it because that part of their brain is damaged or not functioning properly. All right. So that's a great example of how biology affects your behavior. If you damage parts of these brains or you inherit genes that don't connect them as well or as much, that can greatly impact what your ability or behavior is. All right. Same with other parts of the prefrontal cortex. This is basically where your intelligence is, because intelligence is kind of just your ability to achieve a goal in spite of obstacles by using your understanding of rationality and truth, right? So again, like my example, if I got to go home, if I didn't have a car and I'm teaching, I would have to overcome some obstacles to get home. That's kind of what intelligence is. It's your ability to think about the problem that's stopping you, your obstacle in your way, and how to most effectively get around it using truth-based options and rationality to do that. That's kind of, it's a simplified version. That's kind of what intelligence is. Pretty much all that happens up here. So if I damage that, depending on which part of it I damage, I could lose or reduce my ability to do that. All right, and that can definitely happen to people. So, do you think my genes have an impact on how my brain is laid out? Or are all people's brains the same? They're just stocked the same, and it depends on what they learn and what happens to them outside that determines how good they are at things. Which one do you think it is? It's a little bit of both, but it's definitely more so, if you're talking like ability, it's more so leaning towards the biological gene portion. Now we can, like I told you guys about the womb, you can have impacts from hormones and teratogens. Those are epigenetic, right? Those are environmental things that change your genes. But largely, things like your interests, like things you like doing, your intellectual ability, because it's mostly in the prefrontal cortex, and your temperament. So like what you characteristically do, how you react to things, like how quickly you get angry, how patient you are. Most of those things are much more closely tied to genes than anything else. All right. And before I tell you how with the brain, because I don't have time for that, I'll do that tomorrow. Before I tell you how that looks in the brain, how would I know that genes are actually a bigger impact on things like intelligence, personality, and temperament than my environment? How could I know for sure that those are bigger impacts? Anybody know? They figured this out a long time ago, and there's a lot of evidence for it. Okay. I got a brother. He's 2 years younger than me. He's pretty similar to me. All right? We are different, but we have very similar interests. We have similar mannerisms. Our personalities and intelligence are relatively close. How would I know if that was because of our genes or because of my upbringing from my family? Would I be able to distinguish that in any way? In the case of my brother specifically, he and I, would there be any way of saying, oh, it's your genes, or oh, it's your environment?
You wouldn't be able to because you guys grew up similar.
Yeah, exactly. We wouldn't be able to. We have the same parents, right? Our genes will be slightly different, but then we have the same upbringing. So it's like, I don't know which one did it. So how could I find out then which one's a bigger factor using clues like that?
So is it like those experiments where they like separate twins?
Exactly. Well, they don't usually intentionally separate them, but yes. So there's a few things that they use for this. So there's, first of all, there's two types of twins, if you guys didn't know. There's identical, and there's fraternal, And then of course you just have siblings, like my brother and I, same mom, same dad. Then you've got even mixes too, like half siblings, like maybe, well, this isn't the case for me, but let's say my parents got divorced, one of them died, they remarried, and then my brother is from a different mom or had a different dad. We would be half siblings, right? Because we have the same mother or the same father, but the other siblings are, so you got half siblings. And then you've got no family connection. So no familial connection. All right? That's kind of how you can break people up as far as if we were to be raised together. Okay, this would be an adoption, by the way. So somebody, let's say my parents, I don't know, they decided they wanted to adopt for their second kid. So my brother was adopted, totally different set of parents, not related at all with genes. All right. Before I go over this, I've kind of made this in order of, these are actually tied, by the way. I kind of made this in order of how similar our genes are, like as far as me and my brother in this case go. All right, what does it mean to be identical twins?
You look the same.
No, it's not just look the same, although they do end up looking the same. What?
You act this.
That's true too. Hold on, I'm asking if this is the least similar genes, this is the most similar genes, why are these genes the most similar? Talk about the twin itself and the genes. Sounds like you guys don't know. Okay, here's the difference. Identical twin means I have the exact same genes, or almost exact same genes, as my twin. And that happens when, and this is really rare, when the sperm combines with the egg, turns into one person generally. Sometimes, after the sperm goes in and they make your new DNA combo, that is you, congratulations, there's your, we'll just say you're a guy, XY. That's the same genes. Sometimes, super rare, this single cell can split into two. And the genes are what? Different? They're the exact same. That's identical twins. Now this grows into a human and a human, right? Two boys in this case. All right, they'd have the same genes. Fraternal twin means, just based on timing or whatever, the time that the sperm and the egg combine, there happened to be two eggs in the fallopian tubes. I'm screwing up my anatomy. Fallopian tubes, the ovaries, whatever. They combine differently. So let's say, we'll just stick with boys in this case again, to keep it simple. There's an X and an X, that's the egg. The sperms come along, and you have two different ones. Look like eyes. So this is a whole different set of DNA, right? A different sperm came and touched to a different egg. So that's two different sets of genes. And then they grow up, and they become twins. Are their genes exactly the same? No, they're not. It's the exact same difference as if between siblings. So my brother that's 2 years younger than me, we have the same DNA similarity as fraternal twins do, because it's two separate sets of DNA. Two different X chromosomes, and in this case, two different Y chromosomes. So different, all right? Why is a half sibling less similar genetically than a full sibling? Yeah, the other parent gave it a whole new set of DNA, right? So this, it's like both parents contribute half, and then you get kind of like a dice roll as to which ones are active. For the half sibling, that would be different parents, a whole different set of genes. Adoption, two completely different sets of genes. All right, so as we go down, this is almost 100% the same. This is about 0% the same, right? Going all the way down. Bell's gonna ring, and we'll pick up there tomorrow.
So we talked about how genes can determine the structure of your brain, largely. Structure.
Obviously, there can be environmental influences like epigenetics we talked about, your mom's exposure to hormones or other teratogens that could change your gene expression and change your structure. But the code, the imprint, the blueprint you get from your parents largely determines which regions your brain develop, which regions of your brain develop and how many neurons they have, how densely they're packed in, and those things to the structure. But environment, absolutely, your use of those things maintains it, and it can definitely sharpen it, those neurons. Okay, so we used this information to really figure out, at least have a much better idea of how behavior actually happens. So here's an example. We'll use the likelihood that somebody
would yell at a sports game. Like the first person to yell, by the way. Not just like everyone's yelling and cheering. Like the first person to clap, you know, because there's always that chance that you clap and then no one else claps, and then you're like, oh. But, you know, the first person to like yell out in a crowded room during a meeting or something like that, all right? So it's not just like I can look at someone's genes and be like, oh, look, they have this gene. That means they'll be the one that speaks up. It's not that simple, because it's an interaction. Remember, your brain's like an organ. So let's pretend that you're at some sort of meeting, and there's like, I don't know, 100 people there. And the person giving the presentation says something that is wrong. It's mean. They make a mean comment about somebody or something like that. Can we all agree that those 100 people there, they have a different probability, likelihood, that they'll be the first one to speak up? Can we agree on that? Or is everybody equally likely to say, no, that's wrong? No one is, right? It's all gonna be different? Okay, cool. So how does that work, roughly? Okay, so if somebody hears something mean or wrong, that's gonna make them feel probably more aggressive, at least a little bit, wanting to speak up and defend themselves or somebody else, whoever was insulted by this. All right, where does a lot of my aggression come from? Your childhood. Yeah, but like what part of my brain? We talked about this. Fear and aggression, a lot of that's coming from, it's in my limbic system. Amygdala, there you go, cool. So, and I'm not saying that's entirely where it's from, but that's partly where it's from, all right? So I've got a brain, my amygdala's in there in my limbic system, all right? Just because my amygdala sends the signal, I'm angry or aggressive, that doesn't mean it just happens, right? What else has a say as to whether or not you are going to speak up or do something aggressive? Yeah, your frontal lobe, right. Are cool. So ventromedial, for example, but we'll just say frontal lobe to keep it simple. All right. So there's at least two factors there, right? There's my amygdala sending the aggression signal, and there's my frontal lobe, which can apply the brakes potentially, see the situation, and hold back. Okay. So your genes are going to determine largely how many neurons are in each of these areas and how big these areas may or may not be and how densely those neurons are packed in, okay? So depending on how many neurons and how densely my neurons are packed in here and potentially here, that's going to determine or at least change the probability of me speaking out first indignantly, like, you know, upset about what they said, all right? So let's take 3 examples, because there's more than 3, by the way. Let's say, let's just be person 2 because it's going to be in the middle. And then we've got person 1, and we've got person 3. Obviously there's 100 people, and they're all going to have different variations here. But let's stick with that. So there's their frontal lobe. There's their amygdala, right? Frontal lobe, and amygdala's in there, the limbic system. Okay. Let's say this person was born with a super high density and number of neurons in the frontal lobe. So very, very, we'll give him 3 plus him or her for neurons there. All right. So is that going to be a well-developed, strong frontal lobe?
Yes.
Yeah, right. They probably have really good inhibition control, right? Generally speaking. So they got good impulse control. All right. And let's say their amygdala is doesn't have as many neurons in it. All right, I'm oversimplifying, by the way, on how your amygdala works, but I just want to make this point. Let's say this person has just a normal amygdala, size and density, just an average amygdala. So we'll put 2 for that. That'll be average. 2 neurons. Average size, average neural activity. All right. Person 2 here is a different situation. This is somebody who has very little frontal lobe development as far as number and density of neurons. Okay. How's their inhibition control probably going to be?
Not good.
Not as good. All right. And let's say their amygdala is highly developed, like it's large, it's got a lot of activity and neurons in it. Okay. And then this person will be the in-between person, I guess. This is the person with just an average amount of neurons in the frontal lobe, and then an average amount of neural activity in the amygdala. Okay. Which one of these people, if they hear something they don't like at a convention like that, is more likely to shout out something angry in return? 2. Why? Okay, yeah. It's an interaction between the two. So if, for example, this signal is really strong, I'm really mad really quickly, I'm going to have a pretty robust frontal lobe to inhibit this, right? But in this case, this person doesn't. So does it 100% mean that every time this person's angry, they're going to yell out? No. But are they more likely to than this person? Yes. Right, because this person has really good brakes. And their odds of lashing out, their strength of lashing out is just about normal in this case. Or if it was like really low, then it'd be a very weak signal, right? So they barely have any aggression anyway, and their frontal lobe can pretty well handle the inhibition on that signal, right? So this person, since I just switched it, are they more or less likely than person 3 to say something? Less likely, right? Very robust frontal lobe, very weak or very low sensitivity to aggression, so this person is going to be less likely to. Okay, but depending on what's said and the circumstances, there could be a situation where this person speaks out first, right? Because it is going to depend on the contents of the words and maybe their position there, their relationship with that person in particular. Like maybe this person likes the person giving the presentation, even though they said something terrible. You know, they're not going to speak out against their friend, but this is their mortal enemy, and so they're going to say something at some point, right? So it's much more complicated than just, oh, you have a well-developed frontal lobe, you're going to be like this. It's not that simple. There's a lot going on here, and I even really oversimplified just this example, but that kind of gives you an idea. So that's kind of how personality plays out too. Things that you like and ways you react to things. If you're getting really strong signals from one part of your brain and the other one has weaker signals or communication, it's going to be different than somebody who has the reverse scenario, or 2 average ones, or 1 light one and a really intense one. And that's kind of how it works. And that's just one example, right? There's lots of things you like or don't like, and lots of things you do or don't do, and lots of abilities you do or don't have. And it's more like that. It's an interaction between the two, and it's a probability, right? So the probability of this person being aggressive first, higher than the rest. But again, depending on the situation, they might not. Does that make sense? You with me on that? All right, cool. And that's how the genes can play a role in that, okay? Because the intensity and neuron density and use is going to be mostly genetic, but of course your environment has an impact on that, and the situation itself has an impact on that as well. All right. And it could have to do with something as simple too as your knowledge on the subject. Like if I know almost nothing about psychology, and I'm here or at some sort of university, and this professor's giving, we'll just say university, at a university, and a professor's giving a lecture on something, and you hear something that doesn't sound right, you're probably not going to speak out against the professor because they know way the hell more than you do about psychology, and the odds that you are wrong are much higher than this guy who's giving the speech. So that might cause you not to speak up. There's all kinds of environmental, situational influences too. Cool. And these, of course, are going to combine to determine behavior probability or ability. Okay? With me on that? All right, cool. So